De Moivre's theorem for rational indices. In this module, we are going to learn about De Moivre's theorem for rational indices and operations, namely division and multiplication of polar forms of complex numbers. These concepts are explained with various examples and some key remarks associated with it. De Moivre's theorem was invented by the French mathematician Abraham de Moivre. This theorem plays a fundamental role while solving equations containing complex numbers. Without this theorem, it would be very difficult to find the roots of complex numbers, since solving complex numbers in a straightforward manner is a challenging and lengthy process. Some of the applications of De Moivre's theorem include usage related to trigonometry to complex analysis. One of the scopes of this theorem is to find the relationship between the trigonometric functions for multiple angles. It can be applied in order to get the nth root of any complex number. The sum of the infinite series can be determined by using this theorem. The positive powers of complex numbers can be calculated using the theorem. So, we shall now see about operations with complex numbers in polar representation. So, we already know about addition, multiplication, etc., something that we have already seen, but how do we do multiplication with complex terms itself in polar format? That is what we are going to see now. So, suppose, for this we shall need some propositions, and this is proposition 1, Z1 Z2 is equal to R1 R2 cos T1 plus T2 plus sin T1 plus T2. So, this is nothing but, so two complex numbers have been given and both of them are represented in the polar format here. So, R1 cos T1 plus I sin T1 and R2 cos T2 plus I sin T2. How do I do multiplication in this format itself? So, for that this proposition gives the answer Z1 Z2 is equal to R1 R2. So, you are doing a product of the polar radius, whereas the arguments, the angles are added together. So, that is the simplification of this proposition. But what about the proof? So, the proof is quite simple. Z1 Z2 is equal to, just write down all the terms, R1 cos T1 plus I sin T1 plus R2 cos T2 plus I sin T2. And then what do we do? Cos T1 plus I sin T1, when we do the product, you multiply all the terms. So, cos T1 cos T2, I sin T1 I sin T2, but when you do I squared it becomes minus, since I squared is minus 1. Similarly, you while continuing the product, you get all these terms. So, you group the terms, all the real number terms you group together and all the imaginary terms we group them together. So, cos T1 cos T2 minus sin T1 sin T2, and under the imaginary part I have cos T1 sin T2 plus sin T1 cos T2. So, since we all know trigonometry, this should ring a bell, since this can be simplified and written as cos T1 plus T2 plus I sin T1 plus T2. So, this is the format for this. So, it is quite simple to see that this proposition will give you the product of two polar format. Next, for this the remark is, if I have two terms, say Z1 and Z2, when we find the modulus, so modulus Z1 Z2, it is equivalent to saying the product of the separate moduli. So, product the modulus of the two of the product is equal to the product of the two modulus. That is what we can see from this thing. So, modulus Z1 Z2 is equal to modulus Z1 into modulus Z2. So, there is equality here, and also argument Z1 Z2 is equal to argument of Z1 plus argument Z2 minus 2k pi. So, this angle is here due to k. There is if it is 0, it is 0 for argument Z1 plus argument Z2 less than 2 pi, and it is 1 for argument Z1 plus argument Z2 greater than or equal to 2 pi. So, depending on the position, you can assign the value as 0 or 1 for k. So, this is how we do the product of two the argument of the two products, argument of the product of two complex numbers. Now, we shall see an example. Product of two numbers Z1 is equal to 1 minus I and Z2 is equal to root 3 plus I. And for this we find the usual method, finding the polar format. So, R is equal to root of x squared plus y squared, and C, the number is 1 minus I, and it is root 3 plus I. So, this is 1 comma minus 1 and this is root 3 comma 1. Separately we are going to find the values for both these complex numbers. So, for the first one, 1 minus I, the polar radius would be root 2 as calculated from this formula, and the argument or t will be tan inverse of minus 1 by 1 plus 2 pi. Why? Because we have a negative term here, and hence we have a positive x and a negative y, hence we use plus 2 pi. So, this is tan inverse of minus 1 plus 2 pi, which is equal to 7 pi by 4. So, this part is what we have already done earlier, so I am not going to elaborate on it further. We go on to the second term as well. A similar method we follow for Z2 is equal to root 3 plus I. Once again we find R here, we find t to be pi by 6, and then the polar form of Z2 is 2, which is the polar radius, as well as cos pi by 6 plus I sin pi by 6. Now, from the theorem we have seen that Z1 Z2 is equal to R1 R2 cos T1 plus T2 plus I sin T1 plus T2. So, here we are merely substituting the values here. We know Z1, Z2, we know the polar format for both the values. So, this is the polar form for the first term and this is the polar form for the second term. Just write them together. So, root 2 into cos 7 pi by 4 plus I sin 7 pi by 4 into 2 cos pi by 6 plus I sin pi by 6. So, I am doing a product of all the polar radii together. So, 2 into root 2 and then cos 7 pi by 4. Yes, so as you can see here we are adding the terms together. So, T1 plus T2. So, 7 pi by 4 from here and then pi by 6 from the second complex number. So, we are adding those arguments together, 7 pi by 4 plus pi by 6 plus I sin 7 pi by 4 plus pi by 6. So, after doing a little bit of algebraic calculations, we get Z1 Z2 is equal to 2 root 2 cos 23 pi by 12 plus I sin 23 pi by 12. So, this is a demonstration of the proposition that we just discussed. Now, we have the main theorem in this chapter, the de Moivre theorem, something that we will be constantly using henceforth. If Z is equal to R cos t plus I sin t and n belongs to n, then Z power n is equal to R power n cos nt plus I sin nt. So, what we do is, whenever you raise a complex number to the power n, Z power n, R power n. So, this the same way the radius is also raised to the power of n, whereas the angles are amplified by n. So, n here. So, that is the way to remember de Moivre's theorem. But to prove the de Moivre's theorem, we need one more proposition, and that proposition is this: if Zk is equal to Rk cos Tk plus I sin Tk, k equal to 1 to so on up to n, then Z1, Z2, Z3 so on up to Zn is equal to R1, R2, R3 so on up to Rn. This is merely an extension of this theorem. Can you see? So, Z1, Z2, we just did a product of two complex numbers. So, two complex numbers, you got them, you did a product of the two polar radius, and then we just added the angles involved. The same way, if we have to do the product for say n finite number of complex numbers, in that case this theorem works out wonderfully, because you just do a product of all the n complex numbers. Just do for this you need to just do a product of all the n polar radii. So, R1, R2, R3 so on up to Rn. Whereas for the argument, you just have to add all the angles together. So, T1, T2 so on up to Tn. So, all these are added together, and similarly for sine. We will not be discussing the proof of this theorem because it is beyond the scope of the syllabus, but we can just understand that this is an extension of the proposition 1, and we will be using this proposition in proving de Moivre's theorem. So, let us get back to de Moivre's theorem. So, if Zk is equal to Rk cos Tk plus I sin Tk, where k is equal to 1 to so on up to n, then the product Z1, Z2 so on up to Zn would be equal to R1, R2, R3 so on up to Rn cos of T1 plus T2 so on up to Tn plus I sin T1 plus. I have merely written the statement of proposition 2 here. So, this is proposition 2, I have just represented it here. When you are applying proposition 2, what we are doing for R in de Moivre's theorem, we are not having multiple complex numbers. We just have one complex number and it is multiplied many times. So, Z bar n means that you are just multiplying Z many times. So, we are merely applying the same proposition 2 here, except that instead of using it for multiple numbers Z1, Z2 so on up to Zn, all the terms are going to be equal to Z. So, it is Z into Z into Z into Z n times. So, that is what I am doing. So, I am applying proposition 2, but we keep in mind that Z is equal to Z1, Z1 is equal to Z2 so on up to Zn. So, now when I apply, this is equal to Zn. Since all of these are equal terms, this is Z bar n, and on the right hand side, once again the polar radii are not going to be different, it is going to be r throughout. So, multiplying r n times you get r bar n, and on the right hand side in the place of the argument you are just adding the same angles again and again. It is not T1, T2 or T3 or so on. It is merely the same angle added several times over, and hence we are getting T plus T plus T plus T, which is equal to r bar n cos nt plus sin I sin nt. Thus, we have proved de Moivre's theorem. We have used two propositions and we have proved de Moivre's theorem, which will be extremely useful in the following chapters to come, in the following modules to come. So, there is a remark that is in addition to the de Moivre's theorem. So, if Z belongs to C, it means that modulus of Z bar n is the same as modulus Z the whole bar n. So, it makes no difference whether you do the multiplication first and find the modulus, or find the modulus and then find the power n, it is going to be the same. So, this is an extension, this is a direct result of de Moivre's theorem. If R is equal to 1, what happens when the polar radii is 1? Then cos t plus I sin t the whole power n becomes cos nt plus I sin nt. As you can see from this theorem statement, all I have done is I have substituted, instead of r I have substituted 1, that is all. So, this becomes cos t plus I sin t the whole power n is cos nt plus I sin nt, and the same way for argument of Z bar n would be n times argument of Z plus 2k pi, where k belongs to Z. We shall see a demonstration of the de Moivre's theorem. The beauty of de Moivre's theorem is that we can do a lot of complicated calculations quite easily, and as we can see here, we are now going to prove that sin phi t is equal to this term, this expansion, and cos phi t is this expansion. Now, we will use de Moivre's theorem to get sin and cos expansions separately. So, cos t plus I sin t the whole power phi. Now, by de Moivre's theorem, this can be written as cos phi t plus I sin phi t. So, that is equal to, so cos t plus I sin t the whole power phi. If we were to use the binomial expansion, it would come to cos phi t plus phi I cos 4 t sin t plus 10 I squared cos cube t sin squared t, and so on. So, I am sure this is quite easy to follow, because this is merely an application of the binomial theorem. So, just binomial expansion of this term. So, further I do cos bar phi t minus 10 cos cube t 1 minus cos square t and plus phi cos t. So, what I have done is I am just taking all the real terms and I am grouping them together. So, I have taken cos bar phi t and I put it here, and then I have a 10 cos cube t sin square t. So, instead of sin square t, I have put 1 minus cos square t here, and then the other real terms that I can find are this term. So, phi cos t sin power 4 t, but I am writing it as, instead of sin power 4 t, I am writing it as 1 minus cos square t the whole square. Why am I doing this? Is because I want to make my calculations easier, no other reasons. And then I am going to group all the imaginary terms together. So, plus I, and therefore, I have this term cos power 4 t sin t, and the thing is that whenever I am talking about the real terms, I am converting them all to the cos format, and whenever I am coming to the imaginary terms, I am trying to convert even the cos terms into sine terms. So, like this I am just doing the replacements, and then expanding all these terms, I am able to come to this conclusion 16. So, cos t plus I sin t the whole power phi is 16 cos power phi t minus 20 cos cube t plus phi cos t. So, this is the real part, plus I 16 sin power phi t minus 20 sin cube t plus phi sin t, and this is the imaginary part. On the left hand side I am having cos t plus I sin t the whole power phi. So, we can very easily conclude that cos sin phi t, or putting in this term, this is actually equal to this. So, cos phi t should be equal to the real part, and sin phi t should be equal to the imaginary part of this expansion. So, I am just substituting those terms, and that happens to be the proof of this problem. So, I have proved sin phi t is equal to this and cos phi t is equal to this by using de Moivre's expansion. So, this de Moivre's theorem is useful in this particular problem is a useful demonstration of de Moivre's theorem, because imagine if you were to do it in any other way, I do not think you can get the answer in just a short number of steps. So, de Moivre's theorem is helpful when we have bigger powers involved, like in this case we have to the power phi. So, that said, let us move on to the division of two terms. So, let Z1 is equal to R1 cos T1 plus I sin T2 and Z2 be R2 cos T2 plus I sin T2, both of which especially the second one is not non-zero. Since we are talking about division and we do not want 0 in the denominator, we always have this sort of restriction where Z2 is not 0, and Z1 by Z2 would be equal to R1 by R2. So, this is what we will try to prove, cos T1 minus T2 plus I sin T1 minus T2. Now, we have already seen the multiplication of two terms in the polar format itself, right. So, in that case we were just multiplying all the polar radius together and then adding the arguments together. In the case of division, it is sort of different, where we divide even the radii. So, Z1 by Z2 means that the radii are also divided R1 by R2, whereas where in multiplication we did addition, in the case of division we will do subtraction. So, T1 minus T2 and here also T1 minus T2. So, it is very easy to remember this, but the proof is another matter. We need to prove this, although it might be easy when we look at it, we need to still prove it. So, the proof goes like this: Z1 by Z2 is R1 cos T1 plus I sin T1 divided by R2 cos T2 plus I sin T2. The usual method of multiplying by conjugates, and I am multiplying by cos T2. So, the denominator has cos T2 plus I sin T2. Hence, when I am multiplying by the conjugate, I multiply by cos T2 minus I sin T2, both multiply and divide, right. So, you can see that here, and then after which I am going to simplify. The denominator is pretty easy to solve because I have plus terms here and a negative term here. So, it is a plus b, a minus b format. So, it becomes a squared minus b squared in the denominator. So, cos squared T2 minus I squared sin T2, I squared sin squared T2, and this is equal to 1, but we will come to that later. So, cos T1 plus I sin T1. So, the numerator we keep it as such, and this term cos squared T2 minus I squared sin T2, how does it become 1? Because minus I squared becomes plus. I squared is minus 1, so minus into minus plus, and we know cos squared theta plus sin squared theta is equal to 1. So, this becomes 1 and just the numerator part remains. And now I am going to just multiply all the terms together. So, cos T1 into cos T2, cos T1 into minus I sin T2, and then plus I sin T1 into cos T2, and then I sin T1 into minus I sin T2. After multiplication, I am grouping all the real terms together and all the imaginary terms together. So, I can see cos T1, cos T2 plus sin T1, sin T2 are the real terms, and the imaginary terms are sin T1 cos T2 minus cos T1 sin T2, as you can see here. and clearly this is merely cos T1 minus T2. We know that from trigonometrical ratios, and this is actually sin T1 minus sin T2, sin A cos B minus cos A sin B format. So, I am just substituting that, and hence I have proved my statement. So, if I have Z1 by Z2, the way to go about it is divide the two polar radius and then subtract the arguments whenever we are working on the cos and sin part of it. So, this is the theorem or the proposition by which we will do division in polar format. We shall see a remark related to this proposition. So, modulus is an important function in the complex terms. So, modulus is mostly to do with a distance function, and so Z1 is R1 cos T1 plus I sin T1 and Z2 is R2 cos T2 plus I sin T2. Then the modulus is merely R1 by R2. So, modulus Z1, the whole modulus is the same as modulus Z1 by modulus Z2. So, they get and the argument part is Z1 by Z2 is argument Z1 minus argument Z2 plus 2k pi, so to sort of allow for all that multiple valued functions. So, 2k pi where k belongs to Z. So, this is something that you need to keep in mind, and next we shall see an example to compute the value of Z, and where we will be using de Moivre's theorem and the polar format and divisions. Particularly here we will be using this division as well, the one that we just saw, this proposition. As I said earlier, de Moivre's theorem is extremely useful in the case of higher powers. So, when I have power 10, power 5, etc., it becomes very tedious to do certain calculations, and de Moivre's theorem is a savior at that time. And you can see that for the polar form 1 minus I am not going to do this in detail, because we have repeatedly shown you how to convert a rectangular form of number into a polar form of number. So, I am just merely going to assume that you already know all this. So, 1 minus I is equal to root 2 cos 7 pi by 4 plus I sin 7 pi by 4, and root 3 plus I is 2 cos pi by 6 plus I sin pi by 6. I am just converting this Cartesian and this rectangular coordinate into a polar form, that is all. This complex number has been merely converted into the polar form, and 1 minus I root 3 is this term. Now, I need to use all of this, and I am going to write this in this expression. So, instead of 1 minus I the whole power 10, I need to substitute this. So, root 2 cos 7 pi by 4 plus I sin 7 pi by 4 the whole power 10. So, I have substituted that here, and then I have root 3 plus I the whole power 5. So, that also I have so instead of root 3 plus I am substituting this and the whole power 5 as per the problem, and then it comes the denominator. Here also the power is 10. Here we are going to apply the de Moivre's theorem, and you can see that 2 power 5 it is very easy, because root 2 the whole power 10 will become 2 power 5, and then I am merely applying this 10 just is multiplied into the numerator part of this. So, 70 pi by 4, and here also 10 into 70 into 7 pi by 4 will become 70 pi by 4. So, it is nothing but cos theta plus I sin theta the whole power n means cos n theta plus I sin n theta. I am just multiplying by n, the argument is multiplied by n, and then here it is 2 power 5. So, here there is 2 the whole power 5. So, radii is put to the power of 5, and then cos pi by 6 plus I sin pi by 6 you just multiply by the powers. So, 5 pi by 6, and here also 5 pi by 6, and likewise in the denominator. So, on simplification we will do a bit of simplification, we cancel and all. So, there is 70 by 4 can be simplified to 35 by 2, and here no further simplification, and here too no further simplification. I can now this is multiplication of two terms, we remember, right. So, what do I do with the multiplication? We merely add the arguments together. So, here it is 35 plus 35 by 2 plus 5 by 6. Now, if you do the LCM, all the mathematics, you will arrive at cos 55 pi by 3, and the same goes here, because they are the same. So, 35 by 2 here and 5 by 6 here as well. Once again 55 pi by 3, and in the denominator it remains the same. And as I can see, because since these terms can be cancelled, how? Because now it is division. Now what do we know about division? It is 55 pi. We merely subtract the arguments. So 55 pi by 3 minus 40 pi by 3, and then here it is 55 pi by 3 minus 40 pi by 3. It gets cancelled and we are arriving at cos 5 pi plus I sin 5 pi, which is equal to minus 1. So cos 5 pi, we know it is the odd powers, the odd multiples, cos pi is minus 1. So odd multiples, it becomes minus 1, whereas sin pi is always 0. So the value of z is minus 1. In this module, we have discussed de Moivre's theorem for rational indices and operations such as division and multiplication of polar representation of complex numbers. These ideas were examined with a number of illustrations and some significant observations. If a learner is interested in exploring more of these concepts, they can refer to the script in which additional examples have been covered. I hope that these examples and theorems were useful in understanding the concepts of polar representation as well as the rational indices as well as the application of de Moivre's theorem. Thank you.